Our everyday world is governed by the familiar laws of classical physics. Objects have definite positions and speeds. We can predict their movements with certainty. However, at the subatomic level, a stranger set of rules takes over quantum mechanics. In the quantum realm, particles like electrons and photons behave like waves. They exist in a haze of probability, their properties undefined until measured. Imagine a coin spinning in the air, neither heads nor tails until it lands. That's the essence of quantum superposition. One of the most mind-boggling aspects of quantum mechanics is the Heisenberg uncertainty principle. This principle states that we can never know both the position and momentum of a particle with perfect accuracy. The more precisely we measure one, the fuzzier the other becomes. This inherent uncertainty isn't due to limitations in our instruments. It's a fundamental property of the quantum world, a world where certainty gives way to probability, and the act of observation influences reality.
Indeed, the quantum world challenges our classical intuitions, revealing a reality that is both fascinating and perplexing. Quantum entanglement is perhaps the most bizarre consequence of quantum mechanics. It's a phenomenon where two particles become linked, even across vast distances. Imagine two coins flipping and landing on opposite sides of the universe. This is entanglement, but on a quantum scale. When two particles are entangled, they share a special connection. Measuring the state of one particle instantly determines the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein famously called it, seems to defy the limits of space and time.
Let's say we have two entangled photons, the particles that make up light. We measure one photon and find it spinning clockwise. Instantly, we know the other photon must be spinning counterclockwise, even if it's light years away.
This instantaneous correlation is what makes entanglement so perplexing and profound. The implications are staggering. It's as if the two particles are communicating faster than the speed of light, violating one of the cornerstones of Einstein's theory of relativity.
Einstein, though a pioneer of quantum theory, was deeply troubled by entanglement. He believed that the universe should be governed by local realism. This means that objects can only be influenced by their immediate surroundings, and no information can travel faster than light. He proposed that hidden variables, yet unknown factors, were responsible for the seemingly spooky correlations in entanglement. These hidden variables, he argued, predetermine the particle states from the outset, eliminating the need for faster-than-light communication.
In the 1960s, physicist John Bell devised a brilliant way to test whether Einstein's hidden variables or the strangeness of quantum mechanics was correct. Bell's theorem, as it came to be known, provided a set of inequalities that could be experimentally tested. If Einstein was right, the inequalities would hold true. If quantum mechanics was correct, the inequalities would be violated. The stage was set for a showdown between two of the 20th century's greatest minds.
The experimental verification of Bell's theorem is a triumph of modern physics. Starting in the 1970s, physicists conducted increasingly sophisticated experiments using entangled photons. These experiments aimed to close loopholes and address potential biases that could skew the results. The results were clear and consistent. Bell's inequalities were violated. The experiments confirmed the predictions of quantum mechanics, demonstrating that the correlations in entanglement were too strong to be explained by any local hidden variable theory. These groundbreaking experiments, often using pairs of photons generated through a process called spontaneous parametric downconversion, provided compelling evidence for the reality of entanglement.
The universe, it seemed, was even stranger than Einstein had imagined.
Section 5. Quantum entanglement in action, from teleportation to computing. Quantum entanglement, once a theoretical curiosity, is now being harnessed for practical applications.
One of the most promising areas is quantum computing, which leverages the bizarre rules of quantum mechanics to solve problems that are intractable for classical computers.
Entanglement plays a crucial role in quantum computing by allowing qubits, the quantum equivalent of bits, to be linked together. This linkage enables quantum computers to perform computations in parallel, exploring a vast number of possibilities simultaneously.
Another exciting application is quantum teleportation. Despite its sci-fi connotations, quantum teleportation doesn't involve beaming matter across space. Instead, it's about transferring quantum information, the state of a particle, from one location to another, using entanglement as a resource.
Imagine Alice and Bob share an entangled pair of particles. Alice wants to send Bob the state of a third particle. By performing a series of measurements on her entangled particle and the third particle, and then sending the results to Bob, Alice can allow Bob to recreate the state of her third particle on his entangled particle.
The instantaneous connection implied by entanglement is one of its most perplexing aspects. Does it mean that information is traveling faster than the speed of light, violating one of the fundamental tenets of modern physics?
The answer, it turns out, is more nuanced. While entanglement does establish an instantaneous correlation between particles, it doesn't allow us to send information faster than light.
Why is that?
The reason lies in the probabilistic nature of quantum measurements. When we measure the state of an entangled particle, we instantly know the state of its partner. However, the outcome of our measurement is random. We can't control which state we'll observe, and therefore we can't use entanglement to transmit information instantaneously.
So it's like, think of two people, each given a sealed envelope containing a random number. If one person opens their envelope and sees the number 5, they instantly know the other person has a different number. However, they couldn't have used this knowledge to send a message faster than light.
Exactly. It's a fascinating phenomenon, but it doesn't break the cosmic speed limit.
Quantum entanglement challenges our fundamental understanding of reality in profound ways. It forces us to confront the possibility that the universe is not a collection of independent objects separated by space and time, but rather a deeply interconnected web of relationships.
The idea that two particles can be linked across vast distances, their fates intertwined regardless of separation, is a radical departure from classical physics. It suggests that our everyday notions of locality and separability may be illusions, artifacts of our limited perception.
Entanglement also raises profound questions about the nature of time. If two events can be correlated instantaneously, even across billions of light years, does it imply a deeper level of simultaneity, a cosmic now that transcends our ordinary experience of time? These are questions that physicists and philosophers are still grappling with.
Entanglement, by its very nature, pushes us to the edge of what we think we know about the universe and our place within it.
The exploration of quantum entanglement is still in its early stages. As we delve deeper into its mysteries, we can expect to uncover even more bizarre and counterintuitive phenomena. This ongoing research holds the potential to revolutionize our understanding of the universe and drive technological innovation for decades to come.
Quantum computing, powered by entanglement, promises to solve problems that are currently impossible for even the most powerful classical computers. This could lead to breakthroughs in medicine, materials, science, artificial intelligence, and countless other fields.
Quantum communication networks, leveraging the secure nature of entanglement, could enable unhackable communication channels, revolutionizing privacy and security in the digital age. And as we explore the cosmos, entanglement might even play a role in understanding black holes, the early universe, and the fundamental nature of space and time itself.
Quantum entanglement, once relegated to the realm of theoretical physics, has emerged as one of the most intriguing and potentially transformative discoveries in modern science. Its strangeness continues to captivate our imaginations, forcing us to confront the limitations of our classical intuitions and embrace the profound weirdness of the quantum world. As we delve deeper into the mysteries of entanglement, we embark on a journey into the heart of reality itself. It's a journey that promises to challenge our assumptions, expand our horizons, and ultimately reshape our understanding of the universe and our place within it. The future of science, it seems, is entangled with the fate of this enigmatic phenomenon.